So now it's time to start looking at the derivatives of our trig functions. These derivatives can be derived using the definition of limit, but that's very time consuming. There's no harm in seeing it done once, just to know that it can be done, have an idea of how it is done. But these derivatives must be memorized, pure and simple, unless you want to spend an inordinate amount of time on every problem you work from this moment forward. You have to memorize these derivatives. Now, I'll sort of walk through one of them by hand, but before I do, there's a couple of limits that are going to come up that I want to go ahead and mention. If you look at the limit as theta approaches 0 of sine theta over theta, I want to talk about this one for a minute. All right. With this one, you can do a geometric argument. It's kind of long and complicated. I prefer to take a look at this on the calculator. What I'm doing on the calculator here really can't be called a proof. It's just sort of a mathematical way of convincing yourself that it's right. And the geometric argument that they choose to go with is long and drawn out. There is another procedure. There is something called L'Hopital's rule that we will eventually see. And L'Hopital's rule makes very short work of problems like this. But before we actually take a look at this limit, there's something I need to mention, especially when it comes to the trig functions and their derivatives. When we talk about, in a calculus setting, when we talk about a trig function, we always assume that we're talking about a trig function that is defined in radian measurement. Right, so I may not have said this before. I'm pretty much sure that I haven't said it before. But when it comes to calculus, things must be done in the form of radians. And I can't emphasize that or not enough. Degrees have no place in a calculus classroom. You will find that engineers, just as an example, often, very commonly, use degree measure. But if you watch an engineer do his or her work, you will find that if they're working in degrees, the minute they get to the calculus portion of a problem, they switch to radians. All right, and I'm going to try and show you why. All right, so we're going to try and look at the limit as theta approaches 0 of sine theta over theta. So I'll hit equal to. I'll put in, of course, the problem says theta. I'm going to use x's because that's what the TI uses. So I'm going to put in a sine of x over x. And what I want to look at is what happens when the x, or in the context of the original problem, the theta, approaches 0. All right? So the first thing I want to do, I'm going to hit the mode button. I'm going to do this in degrees. I'm going to do this in radians first, because as I just said, degrees have no place, and I want to show you what happens in radians, the correct way to approach this, and then I'll show you what's going on in degrees. All right, so I want to first look at a graph. So I'm going to do a zoom trig, see if it'll give me a decent picture, and that is a pretty good looking picture. That is what sine x over x or sine theta over theta should look like. I'm going to hit the trace button, and as you can see, at 0, at the x value of 0, the function's undefined. And as a matter of fact, you could emphasize that by putting a 0 into a table, and it'll simply give you an error message. And of course, the function's undefined. Putting a 0 in the denominator here means division by 0. So we don't expect it to be defined. But again, looking back at the graph, if I were to zoom in just a little bit, again, that hole in the graph, that undefined spot, isn't really even visible. If I hit the trace button and I move just a little bit to the right of the 0, I get a 0.9998. Move just a little bit to the left of 0, I get a 0.9998. All right, so it would appear to me that sine of theta over theta as theta approaches 0 equals 1. This is a handy limit to have. It's a good one to know. It comes up from time to time, so memorize it. All right, now, as I mentioned, trig functions should be, calculus should be dealt with in radians. Trig functions should be in radians. So if we were to say what's going to happen if we go to degrees, well, I'll do my zoom trig all over again. And of course, you get a graph that is of basically the same shape. It doesn't even want to show it to me. Let's see if the zoom fit will do a better job. Here it is. You get a graph that is of basically the same shape. A little bit exaggerated there. But if you hit the trace button, again, it's undefined at 0. But if you move just a little bit to the right, and if you move just a little bit to the left, instead of getting close to 1, you're getting close to 0.0174. And I'm not even going to talk about what that number is or what that represents, other than say it is wrong. That is not our limit. So you need, again, for the purpose of calculus, to set your calculator and your mind to radians and keep it there. All right? So the first limit that we're going to bump into that we need to be able to evaluate is sine theta over theta. All right? Now, another one that we will run into is going to be the limit as theta approaches 0 of cosine theta minus 1 over theta. And this is another one where if you just plug in the 0, you get division by 0. So we will again resort to using the calculator. So in parentheses, I'll put cosine of x. Don't forget to close the parentheses on the variable there. Minus 1 all over x. Again, I'll do a zoom trig. I'm hoping that this will work well since I'm back in radian form. And as you can see with this graph, if you hit the trace button, when you get close to 0 from the left, you get close to 0 from the right, your y values are coming in, as we can see on the graph, towards the 0. So this limit is 0. Again, not real easy to demonstrate, but as soon as we have L'Hopital's rule, it will be actually very easy to demonstrate. So if, with those limits behind us, with them available for us to use, if f of x was equal to sine of x, what would f prime of x be equal to? Well, let's try it with the definition. F prime of x would be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, which for this f of x, that would be the limit as h approaches 0 of sine of x plus h minus sine of x all over h. All right, now remember with your sine function, you have sum and difference identities. This is the limit as h approaches 0. And the sine sum identity goes sine, cosine, cosine, sine, and it's an x and an h. And since this is a plus, it's a plus, and it's an x and an h. And don't forget the sine of x that was already there on the end, like so, all over h. And it's just your sum identity for the sine function. Now we are going to split this fraction up because I would like the sine function to become a GCF while the two limits that we talked about show themselves. So I want, in particular, I want sine of x to become a GCF. So I'm going to split it up like this. Sine of x cosine of h minus sine of x over h. So basically I've taken this term and that term and put it down here, plus the cosine of x sine of h over h. Right now here, sine of x, I've forgotten the x there. Now factor out, leaving me cosine of h minus 1 all over h, like so. And over here, just to make it visually, put a visual emphasis here, cosine of x comes out. I've got a sine of h over h. All right. Now, I'm going to make use of my two limits. Cosine of h minus 1 over h as h approaches 0 is this limit right here. The name has changed. It's a theta here and h down there, but it's the same thing. So this is going to be a sine of x times a 0. And again, the name's changed, but this limit, the sine of h over h, is this one up here. And this is going to be a cosine times a 1. So that turns out to be cosine. All right, so what we've learned from this is that the derivative with respect to x, sine of x, is equal to cosine of x. Now, as far as these derivatives, again, I can't emphasize enough, you do not ever want to have to sit and prove these every time you use them. That would be unimaginably time consuming. So here's what you need to gather from this section. There are 6 derivatives that you need to memorize, period. Just memorize them. And here they are. The derivative with respect to x of sine of x is cosine x, as we just said. Derivative with respect to x of, I'll not repeat myself, of cosine of x is going to be equal to a negative sine x. The derivative with respect to x of a tangent of x is going to be a secant squared of x. Derivative with respect to x, cotangent of x, is negative cosecant squared of x. Derivative with respect to x of secant of x is secant of x tangent of x, and the derivative with respect to x of cosecant of x is negative cosecant cotangent. All right, now there's a bit of a pattern to these. Notice when you take the derivative of a function, there's no negative sign. Take the derivative of the cofunction, you get the negative sign. In other words, derivative of sine, no negative. Cosine, you get a negative. Derivative of tan, there's no negative. Derivative of cotan, you get the negative. Derivative of secant, there's no negative. Derivative of the cosecant, you have the negative. Also, when you take the derivative of a function, cofunctions tend to show up. And when you take the derivative of cofunctions show up there. Well, cofunctions show up there as well, but again, with the derivative of tan, you get the secant. When you move to the cotan, you get its cofunction. Cofunction of the previous is what I should have said it. The derivative of secant, it being a function, you have secant tangent. The derivative of cosecant, you get these cofunctions. And again, that happens a lot. Right? Take a derivative of a function, you often get cofunctions. So, however you need to do it, these 6 derivatives, among many others that we will see in the future, these must be committed to memory. And again, remember, when you're taking the derivative of sine, you get cosine only if you're in radians. When you take the derivative of cosine, you get negative sine, but only in radians, etc. All right, so always be aware of that. Other than that, all of your previous derivative rules hold true. Okay, so if I had an f of x equaling 3x squared minus 2 cosine of x, and here we're asking for f prime. All right, so I'm going to use a power rule. 2 comes down. 3 times 2 is 6. Power drops. Minus 2 times. Derivative of cosine is negative sine. A little bit of cleanup here. Negative, negative, make a positive. And that's it. And that's it. Again, all your other previous rules hold true. If you had a h of theta equaling cosecant theta plus e to the theta cotangent theta, you want to know what's h prime. Well, using the rules as I've laid them out up here, derivative of the cosecant be a negative cosecant theta cotangent theta plus, and what's going to happen over here, it's going to be a product rule. All right, so first, derivative of second. Derivative of cotangent would be a negative cosecant square theta plus second, which is cotangent theta, times derivative of the first, which is just e to the theta. And there is a little bit cleanup. It can be done. This negative can be brought out front. As a matter of fact, go ahead and just turn that to a minus. And for that one, that's about all the really meaningful cleanup that could be done. I don't have any like terms, don't have a good reason to even attempt factoring. So again, all of your previous rules still apply. And all of your previous rules still apply. So again, just remember those 6 derivatives and you're off to a good start.